Okay, we shall start the session. Good morning, all. I welcome you for the day 5 session on FEM modeling of Cree fatigue crack by Dr. Abhishek Tiwari, Assistant Professor IIT Rupa. So, before starting the session, let me briefly introduce the speaker of the day. He is currently working as an assistant professor in IIT Rupa, and he has done his PhD from Homi Bhabha National Institute of Research Center and MTech from IIT Kharagpur, and he has done his BTech from MNIT Jamshedpur. He has been worked in several places. He has postdoctoral research in Eric Skim Institute of Material Science, Austrian Academy of Sciences, Austria. He worked as a lecturer in the Department of Metallurgy, Rajiv Gandhi University of Knowledge and Technology, Andhra Pradesh, as a project engineer in the Institute of Plasma Research, Gandhinagar, and engineer quality control and assurance in SR Steel Hazira Limited, Gujarat. He is recipient of several awards like Institute Silver Medal, IIT Kharagpur, first winner of Tata Steel Sanitary Rolling Trophy in 2006, and he has also received the IIT DAD Fellowship in the 2011-12. He has one patent and 20 plus international SCI journals to his credit. So with this brief introduction, I welcome Dr. Abhishek Tiwari to take over and start his presentation. Thank you.
Thank you, Dr. Randhir. I hope I'm audible and I will now share the presentation.
Yes, you are audible.
Okay. So, thank you for this introduction. And you can see on the screen is the image of the campus of IIT Rupa. So we have two more pillars like this, which you can see in this picture on the other side. And we have this structure which represents the three visions of IIT Rupa. And different people have different interpretation of this structure. To me, it looks like screw dislocation, and these structures look like simple cubic structures. So I can say that my institute is also representing in some way the department also. And this is Satish Dhawan block, where the Department of Mechanical Engineering and my department, Metallurgical and Materials Engineering, are sharing this building. And very soon we will be moving to a fancier building. And if you want to walk from IIT Rupa to MNIT Jaipur, then you will be going vertically down south, and it will take 101, 102 hours to reach Jaipur, which is also a very nice and established city. I have been there, and it's a good place. Roopnagar is also has some historical importance. So first site of Harappan civilization is here. So if you manage to come to this place, you should be seeing those places. Also, there is a village of Bhagat Singh nearby, and then we also have our beautiful campus. So with this, well, the title, I believe, is it the same? I believe so. So the title is misspelled. So we will be talking about the FEM modeling of creep fatigue crack growth. So some of the slides I have explained before in a previous talk in MNIT Jaipur, but because the audience might be different, I'll be explaining a little bit of those again. So when there is a crack in the system, we want to find out what is the driving force for the crack so that we can manage to understand when a crack will propagate and with what ease it will propagate. So there have been different parameters. For example, in 20s, Griffith gave his parameter by doing experiments on brittle materials, glass, and he simply examined that the amount of energy which goes in the material must be used somehow to create the new surfaces which forms during a crack propagation. So very brittle material will not dissipate energy in the plastic form. So that part was missing in Griffith's idea, although in his original paper he has talked about plasticity also. Then later on in 47, 48 approximately in that period of time, or maybe 54, I'm not so sure about the timing, George Irwin was working in the Naval Organization of USA, and he examined these materials using Griffith's idea and came to know that plasticity brings a significant amount of resistance in the material. So he introduced a correction to Griffith's formula by adding a plastic energy term. Later on, he also described the stress distribution at the tip of a crack using theory of elasticity, to which he brings another plastic zone correction after 10 years of his work on the stress distribution, approximately 10 years. And then for a pretty long time, the formulation which was given by George Irwin and the parameter which is known as stress intensity factor, symbolized with the alphabet K, has been used for a very long time in the field of fracture mechanics. If you look at the field of fracture mechanics, it is not, in comparison to other fields, it's a new field. So it starts basically with Griffith, which was in 20s. So in comparison to other streams of the subject related to this, structural integrity, this field is relatively newer, younger. And then comes the time of James Rice, and he applies this physics that if you have force vector, which is a derivative, which can be defined as a derivative of a potential, and then if you take a line integral of that, you should get a value of 0 if there is no source or sink of energy inside that field. So it works also in the electromagnetic field and other fields. So you have similar integral formulation in those areas also, like you have loop integral of B dot dl in the electromagnetic field. So that formula was used by James Rice to describe this integral, which he named J integral, and I'm guessing because his first name was James. So this is a line integral, and the importance of this is that if you calculate the value of this integral on this contour, let us say the blue circle, and if you calculate the same integral on this green box, you will get the same value, and it will be a non-zero value because there is a source of energy which is in the form of a crack in this contour. If there is nothing as a source or sink of energy, you will get a value of 0. So the advantage of this is that you cannot measure really things at the tip of the crack, and if you do, you will be interfering with the crack's behavior. So the advantage is that if you measure these things far away from the crack tip, you should also be getting the same value, and therefore you can manage to measure the crack's behavior by doing the measurement at a in a far field, so away from the crack tip. Although the experimental value of J integral is not calculated using this formula, but nevertheless, let us stick to this formula for understanding. So W represents strain energy density, and that will be, if it is a displacement control test, it will be the area under the stress strain diagram. Although in a fracture test, you will get a load versus displacement diagram. From that, we are using a correlation factor in terms of eta. You can calculate the J integral in a different, with a different formulation. So W is the strain energy density, dy is the coordinate, so y-axis Cartesian coordinate, and T is a traction vector, which is the projection of stress tensor on the normal vector. So normal will be normal to the contour wherever you are taking it. Del U by del X is the displacement gradient, and ds is a small element on this contour. So with this understanding, let us say that this is a very simple animation. So if you go from A to B, if you calculate a line integral from A to B via different routes, you will be getting the same value. And if you come back and there is nothing, then the value of that line integral will be 0. The formulation of J integral depends on a very important assumption that material is non-linear elastic. And this assumption comes because you have to have the force vector has to be a differentiation of a potential. So you cannot really assume plasticity, and therefore Rice said that elastic plastic material for which the stress strain diagram looks like this red curve can be assumed to be a non-linear elastic material. So initially it is linearly elastic and then it becomes non-linear, but still assume it to be an elastic material only. And then in that case you can have one-on-one formulation for strain and stress. So for one value of strain, you will be getting one value of stress and vice versa. And if that is true, then you can apply the concept of J integral without any invalidity. So this non-linear elastic assumption would mean that if you are loading it or unloading it, for a value of stress, you will be getting one value of strain. But if it is elastic plastic material and if you unload, then for same value of stress, you will be getting more than one value of strain. And there it becomes path dependent, because the value of strain which you are getting while loading is not equal to the value of strain which you are getting when you are unloading. So in that case, this J integral is not valid to be applied. And so we can say fine, as long as we are loading this specimen, we should be okay. But that is not true, because when the crack grows, then the area, the material points which are behind the crack tip, they had a finite value of stress when the crack was there. It did not open. And when crack opened up a little bit, those points goes to a 0 value of stress because they have been separated. And it means that they have been unloaded. And therefore, there is an unloading which goes on behind the crack tip. So J integral is theoretically not valid for a growing crack also. So with these problems, let us also look at path independence. So we have already discussed that when you have different contours, you calculate the value of this integral. For a homogeneous material, you will be getting one value of J integral. And if you look at the linear elastic FEM analysis, the stress distribution will look like this. So this is one Mises, so it looks like a butterfly, and then when it will cross a critical value, the plastic zone will also look like a butterfly. So this is only half symmetric model in 2 dimensions. Now assume that this material 1 is steel, any steel, and it has been somehow joined with another material, which for example you can take as aluminum. So and we also assume that these two materials are deforming only elastically. So material 1 has an elastic modulus of 200 gigapascal, and material 2, because it is aluminum, it should be having an elastic modulus of 70 gigapascal. So there is a drop in the mechanical property in elastic modulus. So what will happen is that for the same amount of strain along this line, because this interface has to maintain a strain compatibility. So you, for the same amount of strain, you will be having two different values of stresses, and the stress in material 2 will be much smaller because the elastic modulus is much smaller in comparison to material 2. And that is what you see in this simulation, that beyond this interface, the stresses are not really of any high value in comparison to what you have on the material 1 side. So what does it mean? It means that for the same amount of loading, if you have a transition of material which are deforming differently to begin with, so in reference configuration, in that case, more energy will be available at the crack tip if you have a transition from a stiffer material, so a material which deforms with a lot of resistance, to a material which deforms with lesser resistance. In that case, you will have more energy available at the crack tip, and therefore it will have a tendency to grow easily if the resistance of the material is crossed. So what have we done? We have just introduced a different material, and you don't have to make this kind of joining. You can place a very small interlayer also, and it will have a little bit different effect, but the energy distribution will change. So by placing a very small interlayer material, we can manipulate the amount of energy which is available at the crack tip. And if you reverse the situation, so if material 1 is giving lesser resistance to the material, then less energy will be available at the crack tip. So that means by placing this kind of interface, you can decrease the amount of energy which is available at the crack tip, and if you can manage to decrease the energy available lower than the resistance of the material, the crack will stop. It cannot propagate. So using this, you can enhance the material's crack resistance. And this is different from mechanisms like fiber bridging and transformation induced plasticity and things like that, because here the crack is getting influenced even at a distance from the interface. So I will not go in that detail. This formula just represents that when you don't have path independence, then the J integral calculated at tip is not equal to the one which you calculate at far, and it differs by a certain amount. It can be positive, it can be negative, and that will give you the idea that how much energy is available at the crack. And now let us look a little bit at the concept of configurational forces. Why are we looking at this idea of configurational forces? Is because we have discussed some problems with the concept of J integral. So we know that if there is a real material which deforms plastically, then J integral is not valid. You cannot allow unloading or non-proportional loading, and that is inevitable. If the crack grows, then there is unloading. So this concept of configurational forces has an advantage that it does not assume anything about the material's constitutive relation. So it can be elastic, it can be plastic, it can be a creeping material, it can be a viscoelastic, any type of material, you can use this idea. And the idea is very simple, that when you have an energy gradient, you have a force. So if you take an interstitial atom which sits in octahedral or tetrahedral void in a crystal, then there, even though it is sitting in a void, there will be some compression from the surrounding atoms, which are bigger in size. And now imagine a situation when this interstitial atom is at the surface. So at least half of the compression is gone. So there is a happy situation for this interstitial in comparison to the place where it is sitting. And therefore there is an energy gradient, and therefore there is a force on it, which will compel this atom to go to the surface. Whether or not it will go to the surface, that's a different story, because then there is a path involved. The atom has to find a path, and then only it can go. And if the path is available, this force should bring the atom to the surface. And this force is configurational force because it is arising by two different configurations of the same atom if they are in a different situation. So the idea has been applied in recrystallization, in polygonization of dislocations, and very recently this has been also applied in fracture mechanics. So we calculate this configurational forces by these formulas, which might look very complicated, but if you compare, these terms are equivalent to what you get in J integral. So phi is the strain energy density, which was represented as W in J integral formula. Phi and W will have some differences. They will have some differences when it is displacement controlled and force controlled. And I is identity matrix, identity tensor, and F is deformation gradient, transpose of that, and S is first Piola-Kirchhoff stress. So this is also Eshelby's energy momentum tensor, the C. And when you take the divergence of that, divergence of any parameter will tell you the inwardness or outwardness of that thing for which you are taking the divergence. So you can imagine this to be some kind of energy balance. So whatever is stored, whatever is applied, if that saturates, then there is no inwardness or outwardness of that parameter. So in that case, configurational force will be 0. And if the balance is not 0, then in that case there will be a finite value of a force vector, and that force is configurational. So configurational forces are calculated in bulk of a material, so inside a material using this formula. At crack tip the formulation and at the surface the formulation is a little different, but we will not discuss that. So how do we calculate the J integral using configurational forces? We find out the bulk configurational forces in a contour, okay? And then we sum all the configurational forces in the expected crack growth direction. So for example, if the crack tip is going in X direction, then you have to take the product, so projection of the summation of all the force vectors along E1 or Ex, the basis vector, unit vector in that direction, and that will give you a scalar value. And that scalar value, if you assume the material is non-linear elastic, then it will be exactly equal to Rice's J integral. And if so here you have a choice. So you can also assume the strain energy density to only consider the elastic strain energy density. And why should we do that? Because plastic strain energy is dissipated. It is not going to come back. Material consumes that energy, and after deformation it is not available for anything to be done by that energy. Only elastic energy can be stored by the material, and it can provide the energy for surface creation. So the J integral of Rice can give you material's resistance, but it cannot describe the driving force on a crack, okay? Because plasticity cannot contribute to the force which can drive a crack. So here we can calculate these forces by two different ways. One is by taking or considering the material to be completely nonlinear elastic. That means counting all type of deformation energy, elastic, plastic, creep, or if any other kind of deformation is involved. And another way is to only count the elastic energy. And when we do that, we give it a little nomenclature. So this is what I was explaining. When you have nonlinear elastic assumption, you take the whole area under stress strain diagram. And when you have only elastic strain energy calculation, then you take the area under this triangle. Okay. And the nomenclature which we give when we only take elastic strain energy density, then we call that elastic plastic configurational forces. Okay, because that is simulating a real elastic plastic material. And if we take the whole energy, then we call it F non-linear elastic, because we are assuming the material to be non-linear elastic, and in that case you will be getting conventional J integral value. In this case you will not be getting conventional J integral value. This value will be different from what you get from Rice's J integral. Okay, and by using a post-processing Python based code, we can calculate those configurational stresses and divergence and all that, and then we can calculate configurational forces, and they are plotted here in abacus. And you can see that these configurational forces are calculated using only elastic strain energy density, and they are tending to follow the plastic zone, because there is a relation of configurational forces with the plastic strain when we only consider elastic strain energy density. So this I already explained, that when you take all the energy, then this is equal to the conventional J integral, and it is path independent. And when you only take elastic strain energy, which you should, then it is not equal to J conventional, and then it is path dependent. Now the question comes that if I'm taking 4 paths, 4 contours, which of the contours should be telling me the value of crack driving force? Because it will become path dependent. Okay. So now we try to slowly go in the direction of creep deformation, and I'll just discuss a common mistake which people do, usually students. And so this is a plot of creep strain versus time at different values of stresses, and although the values might be very small, but the time is going from 0 to 9,000 hours and strain is going from 0 to 0.7. It's not in percentage, it's absolute value, and the stress is increasing as you go up in the curve. So what you observe here is that at a very small value of stress, you have a little bit of, probably, you can't make it from here, but probably there is a primary creep zone, and then there is a linear strain increment with time, and then it becomes exponentially high. This exponential behavior increases as you go up with the stress. Okay, and then what do? You plot, and this data comes from conventional creep test, so there is no crack there. And then what do? You calculate strain rate and you plot it versus time, and this is how it looks like. And I have found that many of the students, they look at this kind of data and they say that, there is no primary creep and there is only secondary creep, because that's how the strain rate diagram looks like. And then it goes, the slope increases, so there is tertiary creep. And they will say that this value is constant, so it is following steady state creep and everything is good. But it is not true. So if you look at this diagram, you will see that steady state creep rate is 0. Okay, but if you just do this, if you just plot on a log scale, then the situation differs, and you see that there is significant amount of primary creep in all of these plots. Okay, so this graph is misleading. If you plot in this way and you say that there is no primary creep, that is misleading. And you have to look at different scales. Here also you can find out primary creep by increasing the scale, or simply just plot it in log and you will see that if there is primary creep or not. Okay, and then this is double log. This is log only on x-axis, on time axis, and then you make it log plot, and then you will see that it becomes very clear. Also the trend, how it, and you see that there is no steady state creep here. Okay, so there is no plateau. It is, the slope constantly changes. So this is a mistake which people do, and also in modeling creep and creep crack, what people do is they assume Norton's law, which has no time dependence. So you only think that, you know, secondary stage creep, if I can model very simply using Norton's law, then that will be it. But that will not be simulating the real materials behavior. How much time do I have? Do I have some time or?
Yeah, Dr. Abhishek, you have still 1 hour.
Okay, okay, thank you.
20 minutes is for the discussion.
Okay,
So you have, in a whole, you have 40 minutes.
okay. That should be enough. Okay. So with that understanding of creep, now let us look at what happens when we have a crack in a material and that material is deforming with time dependence. And in metallic material, we call that creep deformation. So we have looked at J integral, and we also know that J integral comes from one-on-one correlation of strain with stress. So that constitutive relation can also be written in this form. Okay, so strain is dependent on stress with some power law and a coefficient, so coefficient and exponent. And then this J integral is derived and it is path independent and everything is good. In creep, J integral cannot be applied because strain will be a function of time also. So then there is a researcher, Hoff, and Hoff says in 1954 that instead of strain, you have a one-on-one correlation of strain rate with stress. And there is no time dependence if the material is deforming under a steady state. So here he is talking about steady state creep, secondary stage creep, but steady state. So no time dependence. So there is no time parameter here. And in that case, strain rate is a function of stress only. When that happens, you can replace all the terms which are related to strain in the J integral, and you will be getting a cousin of J integral, and a symbol was given C star for some reason. And so here you replace strain energy density with strain energy density, rate of change of strain energy density. So strain energy density is this, okay, and phi dot will be simply this. And you change displacement with displacement rate, and then you get this formula, and then you get this integral, and theoretically it should be path independent as well. But things are not so simple. So when there is a crack, you can have a small creep zone, and then the creep zone will increase in size. You will have a back face creep, and then you will have a general creeping phenomena, which is known as extensive creep. So if you look at small scale creep, the total strain you can break in elastic and creep. Ignore plasticity for now. So you can imagine that the stresses are very small. So there is only elastic deformation and time dependent deformation. So in that case, strain rate will not only be a function of stress, but also stress rate. Okay, because elastic strain, you can change it to sigma by E, and then the rate of change of that will be sigma dot by capital E. So there is a stress rate dependence also. If you happen to have plastic strain, because plastic strain is time independent, the rate of that will be 0. So there is no issue here because of plasticity. So because strain rate is not following one-on-one correlation with stress only, so it's not a single valued function of stress only, you cannot apply that C star integral here. Okay. And some of the researcher has said that very close to the crack tip, because n is usually high. When you calculate n by plotting the log, so you have to do a lot of creep test at different stress values, and then you find out the steady state creep rate, and then you plot those versus the stress value in a log plot, and the slope of that gives you the value of n. This n value is usually much higher. And because this is much higher, the second term dominates. So the first term is very small, and researchers say that you can ignore the first term and you can still apply that integral, but it has to be very close to the crack tip where the elastic strains are very low, because creeping is happening here. So you can't apply a little away from the crack tip. So these are the situations. C star integral, which we discussed here, is only applicable in extensive creep, meaning that you can apply anywhere, no problem. But it will be path independent only when the material is deforming extensively in creep. Okay, so where elastic strains will be very, very small to ignore. So these are the problems with C star, which is not path independent when the scale of creep zone is very small. And the other problem with C star, and there are different similar integrals, is that how have we derived it? We have derived it by replacing some terms because it makes one-on-one value of strain rate with sigma. That's it. J integral had a different derivation. So J integral, if the crack is not growing, so for a static crack, it can describe the driving force on the crack. Okay. But C star or similar integrals are not defining anything. They have no theoretical or physical meaning behind them. They are just integral. They are not defining crack driving force or rate of change of crack driving force, because if J is crack driving force, then rate of change of J will not be equal to C star, and we'll see how. So these are the problem with C star integral, and let us look at some calculations. So as I said that C star is decreasing. So if you do a calculation on using finite element analysis, or you can also do experiment, and you will see that C star decreases with time. So if it was defining crack driving force, then the crack should get arrested because it is decreasing with time. Okay, and after decreasing with time, it stops at a constant value. That means the crack driving force will have a constant value. That means the rate of change of, so dA by dt, which you plot in Cree, should be 0, because the rate of change of driving force is not changing. So why should the crack growth rate change? Okay, but J integral increases. So crack driving force really is increasing with time, but C star is not. So C star is not defining crack driving force. That is established. The two graphs on the below, so these two are for displacement controlled creep test, although that's a weird test to do because you are applying a displacement. So let us say you pull a specimen by 5 millimeter and you fix it so that it shouldn't open more than 5 millimeter, and then you put it at high temperature for metallic materials and leave it for 7,000, 10,000 hours. What will happen? So with time dependence, the material will become softer, so the modulus will decrease and crack will grow. But as crack will grow, the force available will decrease, okay, because you have lesser ligament left for the specimen to bear any load, and therefore the crack will stop after some time. So you will not find much work on displacement controlled creep test in literature. So I have found only one, and I think that was done by Niete et al. So we have simulated that also, displacement controlled creep crack growth, and there you see that the crack driving force decreases, J integral decreases with time, and that really happens in the experiment also, that after some time crack will stop. Another observation which you can see on these plots is that when the timing is very small, so from 0 to 1000 hours, also in the lower one, also in the upper one, you will see that the plots of C star are not one. Okay, so they are different plots, they're different lines. It tells you that these are path dependent for a short period of time. Why? Because in the beginning, creep zone is small, and we know that in a small creep zone, elastic strains are significantly higher. So there is going to be a path dependence in C star. In a larger time scale, creep strain dominate the elastic strain, and the material completely deforms under extensive creep condition, and there C star works very well. Okay, so for a static crack, these simulations are for a non-growing crack. For a static crack, you will get one value of C star in extensive creep condition, and then when the crack grows, you will get different values, and you can plot C star versus dA by dt. And people have shown correlation of dA by dt with C star, which does not make much sense, real sense, because what is C star, then that is a question which cannot be answered. So crack growth velocity is related to a parameter which is not describing crack driving force or materials resistance. Okay. But in some cases, C star can define the stress field at the crack tip. So with this information, you can also look at these two plots of elastic plastic creep configurational forces and non-linear elastic configurational forces. And you see that non-linear configurational forces, they are looking a little bit higher. These two images are taken at the same value of time for a static crack. And why do we call it elastic plastic creep? Because here the total energy includes elastic energy, plastic energy, and creep strain energy. So when you only take elastic energy, we call it FEPC. And when we take all the strain energy densities, then we call it nonlinear elastic, because then it behaves like a nonlinear elastic theoretically. So now let us look at, because C is not a crack driving force, so how can we look at J and rate of change of J? So some people have given some description of rate of change of J integral. You will not find a lot of work on the rate of change of J integral. But Helen in 1991 says that dJ by dt can be calculated as, or can be described as, summation of C integral plus J divided by some values and the rate of change of C integral. Okay. And so dJ by dt should be equal to Ct when dC by dt is 0, when the second term is 0. Okay. And you look at this curve, and Ct has no time dependence in extensive creep. Right. So dC by dt is going to be 0 only. So that means that J is equal to Ct, and this has a bracket. So it means you have to take this C integral very close to the crack tip. So this is not C star integral, but the formula is same. It's just that you take it as very close to the crack tip. So in that case, rate of change of dJ by dt should be equal to Ct, but that is not true. Another formulation by Atluri and Nishioka, there they have done a lot of mathematics, and I'm just including the final form. So you will have the differentiation of strain energy density with respect to the coordinate, and then you will have this term with rate of change of displacement increment with coordinate, and you will have del u by del x term. So at least there are three terms, and then you can just say that dJ by dt equals to limit delta t tending to 0 del j by del t. Okay, delta j by delta t. So if you divide this by delta t, you are seeing that these terms are more than what you have in C star or Ct integral. And you can also do it with your hand calculation, and you can find out that J, if you do the differentiation of J with respect to time, you will not get the expression which is which is there in C star integral. So mathematically, it is established that these two things are not same. Also, theoretically, you can say that, you can see that, you know, J is, so what is happening to the slope of J? Okay. Initially, it is increasing, and then probably it remains constant in this simulation. So dj by dt initially will be increasing, and then it will remain constant. Okay. And here, see, so it might have similar behavior, but not exactly same value. Okay. Now let us come to the real theme of the topic, which was creep fatigue crack growth. So in creep fatigue, what happens? You apply the load in this form. So you load the sample and you leave it for some time. So hold it for some time so that creep deformation takes place. And then you unload it and reload it and then do the same thing over and over again. You can do it in different ways. Okay. You can do it in triangular form also. So you load it and you are doing it at elevated temperature where time dependent strain will happen. Okay. So creep will happen. So the loading also takes some time, right? And in that time part, in that period of time, there will be creep strain also. So you can do it in triangular way. So just remove the square thing from the middle. So you load it, unload it like a simple fatigue cycle, and you will be having some creep also. Okay. You can have it in different ways. You can also do it sinusoidal and other things. But mathematically, it is simpler if you have a trapezoidal form, and this is why you will find a lot of work on trapezoidal waveform. So you load it, hold it for some time where you don't have any cyclic interference of cyclic load, and you only have creep here, and then you unload and do this thing over and over again. And if you calculate CT, then you see that CT values is something like this in this part of the loading, and then the value is decreasing, but the behavior is not. Okay. You can have a different CT behavior. So the values are same and behavior is also same in each path. So in each part of loading. And these two behavior can have different creep zone and plastic zone interference with each other. One case, in the upper case, you will be having creep zone larger than the cyclic plastic zone. And in the lower case, you have creep zone smaller, so embedded inside the plastic zone. Okay, and remember that plastic zone is not time dependent. So what is the parameter here? So here the parameter was proposed by Saxena, and that is the average of CT integral. So you are getting different CT integral in different number of cycles. So you take the average value of that. And how do you take the average? Using this formula. Okay. And when the creep zone is embedded inside the plastic zone, then the formula changes a little bit, but you can derive this formula from this only. Okay. If you have creep zone embedded in plastic zone, then you just remove. So if you can remove n from here, then you will get 0 to th. And because in each cycle you have the same thing happening, so you don't really need to integrate in each cycle. You just integrate in one cycle and divide it by 1 by th, and you will get the CT average value. And then people plot dA by dt average, which I will tell you how that is calculated. And sometimes, so dA by dt average, sometimes the dA by dN is also plotted versus CT average value. Okay. And this shows a trend on a log-log plot. It shows linear trend, sometimes a huge scatter, which you can see. So this is for one type of material only. For different hold period and different loading period, these things are calculated, and you see a very large scatter here. Okay. So dA by dN is calculated by dividing into two parts. One is creep part and one is fatigue part. Okay. So dA by dN, which is coming because of cyclic loading, is calculated by using a formula similar to Paris law. So there is a coefficient, then you have delta K, so K max minus K opening. Why I have K opening? That is probably known to you that when you have compressive loading, that will not contribute to crack opening. Okay, so that's why you only consider anything for the stress which is not less than 0. So K max minus KOP to the power sum. So this is the exponent, this is coefficient. And for creep part, you have dA by dN, which is dependent on dA by dt into the period of time for which the hold has taken place. So in the trapezoidal form, this amount of time in the holding period. And then there is a dominant damage formulation of dA by dN, where you don't add it. You don't add these two terms, but you take the maximum of these two, because they believe in this formulation, it is believed that whatever mechanism is dominating, we should only count that as for the rate calculation. Okay, and Ramirez has done some creep fatigue calculation on CT specimen, and they showed that the opening stress normalized with the opening load normalized with the maximum load, it saturates after certain amount of cycles. Okay, so initially the opening load fluctuates. It is not same in every cycle, and after some number of cycles it saturates, and then they have plotted dA by dN versus delta K, and the behavior looks like this for different hold period of time. So the markers are from experiment and the lines are from simulation. Okay, so we have replicated that experiment which Ramirez has done using node release technique. So how have we done it? We have made a two-dimensional CT specimen of the same dimensions which Ramirez has used, and we can describe. So we don't use the contour which comes in abacus by default, because if you calculate contours in abacus by default, abacus will be making the first contour on one node, single node, and then it will keep on adding a layer of nodes over and over, and it will be making contour paths. So if I want to make a contour which is 5 millimeter away from abacus, and if I have a very refined mesh, so I will have to create, if I'm using default method of abacus, which is an FEM software, so then I will have to tell abacus that I need to make, depending on mesh size, I need to make 500 contours to reach 5 millimeter away from crack tip, because it will be adding one layer after one layer in each contour. So you can imagine that for 500 contours, it will be calculating this integral, and this will be computationally very costly. So you can also define a node set, and you can tell abacus to calculate the contour integral on that node set only. So you don't need to create any crack or anything. You can simply do it by writing some commands in input file. And if you are interested, you can contact me and I can tell you how to do that later on. So that's how we create contours, and we ask abacus to calculate the CT integral and the loading is applied in this fashion. So P minimum is 0.9 kilonewton and 9 kilonewton is the maximum load. 600 seconds is the holding period of time. Loading and unloading takes a time of 2 seconds. And the node release technique is simply, in each step you release one node, two node, or if you want to vary dA by dt, then you can calculate how many number of nodes you have to release in each step, so that you get whatever amount of dA by dt you want. So some researchers have problem with node release technique, because they think that it is an artificial way of growing a crack, and material may not grow the crack in that way. That is true. But even with artificial crack opening, we will be calculating the correct value of CT integral. Why not? So if the material opens with a dA by dt of some value, then it must have the same value of crack driving forces or the stresses at that value of dA by dt. So even if dA by dt part is managed in computation, the value of integrals should not be wrong. So the overall trend should look similar to what you're getting experimentally or by using any other damage mechanism of creep crack growth, creep fatigue crack growth. So again, you release some nodes and crack grows. And मैं talk नहीं हूँ, बाद में call करता हूँ. And so we release some nodes and we calculate the value of CT integral for those cycles. And on this plot, you see crack opening displacement, which is calculated. There can be a sophisticated method of calculating crack opening displacement. But here, a simple method is used that we calculate the displacement on the node just ahead of the crack tip. And because crack tip is moving in node release technique, so it already becomes cumbersome here. Although I would say that there are better methods of calculating crack opening displacement in finite element analysis. And the red markers are showing the force value, which is the scaling is given on this side, on the right hand side of this figure, and here you have crack opening displacement. You see that it sometimes goes in compression during the cycle because, and this is what Ramirez also found, and then it saturates after a certain number of cycles. Okay, so we do need to consider that KOP in the fatigue part, we do need to consider that the stress intensity factor you have to calculate for opening load only, not for the load for which COD is going negative. Okay, so, and then we have plotted the creep zones.
हाँ ऋतिक बोलो.
So we have plotted creep zone size and we have plotted plastic zone size, and you see that because the load is constant, plastic zone is not changing much because that will not show any time dependence, but creep zone, after some time it becomes extensive creep, but there is smaller zone creep also, it has to happen. And then we have calculated the rate of change of J integral, which is calculated from configurational forces. So this is not conventional J integral. The J integral which we talked about, where we only take elastic strain energy density and we don't take plastic or creep energy density. Rate of change of that and the average value of that is calculated similar to how CT integral is calculated. So using this kind of formula. Okay, so we also calculate rate of change of J integral average. So it should not be dJ by dt, it should be dJ by dt average. Okay, so 1 by th, and then you take the integration of delta J dt. And CT average is can be also calculated experimentally using this formula, and can be calculated numerically or mathematically by the formula which I showed in 2 slides back. And then all these parameters, CT average experimental, dJ by dt average value calculated from configurational forces, and CT average calculated from formula, theoretical formula, all of those are plotted on this graph, and you can see that the value of CT average experimental is shown by these blue diamonds marker, and dJ by dt calculated from configurational forces are boxes, and CT average value, which is calculated from the mathematical formula, all of them are following the same trend, except dJ by dt, which is calculated by assuming the material to be non-linear elastic. That value is much higher in comparison to others. Okay, so this says that dJ by dt is equal to CT, so why should we bother about it? We can simply go or continue to go with CT. The advantage here is that CT, when that becomes path dependent, first advantage is that when that becomes path dependent, we do not know which contour is really describing the crack driving force or whatever CT is describing, which essentially it is not describing anything. But if it could, then we don't know which value. So let us assume that dA by dt shows a correlation with C star or CT. Okay, so there is some correlation. Now, if you are getting different values of CT for different contours, which one should be a correct correlation? That question is open. Second advantage is that C star or CT or CT average, all of them has no physical meaning. Okay, they are correlated with dA by dt. That's a line integral. Mathematically, there is no problem. But what is it defining? That question is unanswered. Okay, so if you look at the work which we did on creep here in this plot, if you look, there are different curves for CT integral calculated at 1 millimeter contour, 2 millimeter, 3, 4, 5, 6, 7, and far field. Okay, and all of them are showing path dependence. But dJ by dt we have calculated for different paths, and you can see here also dJ by dt is not plotted in this figure, but you see that for short period when the timing is smaller, there J integral is path independent. It is not showing path dependence much. Later on, when creep strain increases, it shows. Okay, and this is not conventional J integral, this is configurational force based J integral. So we are getting a special advantage in small scale creep where C star is path dependent. In that case, this J integral is path independent, and dJ by dt will also be path independent. Okay, so there we can say that this describes the crack driving force or rate of change of crack driving force, unlike the confidence which you will not get in C star or CT or CT average for small scale creep. Okay, so with that, I believe the topic is over. And at the end, a little bit of advertisement that we made a device so we are also working in the area of healthcare a little bit. And so we have made a mechanical device which can provide the passive motion to the knee joint. So if you have a knee surgery, after that you need to do some physiotherapy. And in order to do physiotherapy, you have to go to a physiotherapist clinic and wait for queue, and your leg is not really good because you have just done your surgery. So you will need some people to help you to go there, and then physiotherapist will also take some money from you, and also you will be dependent on that person, how good he or she is. There are commercially available machines which are motorized with fancy remotes and all, but the thing is they are costly and also heavy. This is very light, and this is also not completely like you have to do it, but half work you have to do with your own hand, but there is no motor involved, so you don't need to plug in, so you can use it in village. And there is no battery also, so there is no electrical equipment in this. So with that, I thank you for inviting me to give this talk in your short-term course, and I would be happy to answer any question if you have.
Thank you, Dr. Abhishek, for giving in-depth knowledge on the creep fatigue crack growth. So the session is open for the question. If anyone has any question, please raise the hand and ask the question. Okay. Okay, if there are no questions, I have one question, Dr. Abhishek.
Yes.
Regarding the quantification, can we do the quantification of this crack growth, whether it is due to creep or due to the fatigue?
Yes. So configurational force has been calculated for fatigue crack growth and creep crack growth very recently.
Okay.
So the recent article has come in IJF, International Journal of Fracture, in this year. So that was the first work on configurational forces in creep condition. Fatigue has already been done long back. And creep fatigue, this work we have submitted. Hopefully the result will come soon. But it can be applied in any type of deformation. So it is away from any invalidity. So any type of material you want to model or any type of loading you have, it will configurational force concept is valid and it can be calculated. For fatigue and creep isolated, so separately it has been done.
Okay. So with the help of empirical formula, we can calculate.
Yes.
That would be. Yeah. Thank you.
So these are
So-
also called material forces, especially by ANSYS group. So we call it configurational forces, and ANSYS have implemented the coding of this material forces in their software. So there you don't really need to do the coding. You can, but I have not done it on ANSYS. I have heard only. So material forces are there, and in Abacus you can do post processing, and those details are also there in a journal in an appendix. If you need more details, I can send you the codes also, which are free but a little slow.
Okay.
Yeah.
Okay. Thank you. Thank you. So if there are no questions, then we thank Dr. Abhishek for giving remarks.
Hey, sir, we are not able to hear you.
So first and foremost, I would like to express and lasted for the 5 days. My deepest gratitude goes to all who attended this short-term course and helped it to be a successful event. The short-term course was to keep updated on the latest developments in the advanced manufacturing process activity that was happening in this field. So we have heard and learned from many of the speakers, as well as audience has also educated by asking several questions on this advanced manufacturing process. It was help us to have a better understanding of the rapid changes that is taking places in the material processing sector. I'm certain that the takeaways from this short-term course will further deepen our thinking and stimulate our research work for future. In my capacity as a coordinator of this event, I thought it would be appropriate and useful to summarize some of the themes and ideas emanating from this short-term course. It will be useful for the research community perhaps to consider some of the issues in the futures. Firstly, the STC short-term course was very effective in meeting the purpose to have an overview of the advanced manufacturing process and also discuss on the future aspects of the advanced manufacturing process and testings of the materials. Secondly, the following themes of discussions, there were a number of lectures and interesting points were raised by the audience. So all of our speakers have given the depth knowledge on the advanced manufacturing process and the following lectures were taken by the various speakers from various institutes. So just to summarize, the day one we have the Drs. Sanmugam Sundaram T, assistant professor from DIIT Pune, who gave a session on the talk on the high entropy alloy processing, followed by Dr. Himanshu Vasista, who had given talk on the advanced welding techniques for the stainless steel. Day two, we have Dr. Anand Kumar for application of additive manufacturing in strategic sector. And in the afternoon session, we have Dr. C. Paul, who gave talk